Right, this is actually my third attempt at this, which is good fun. I had put an entire video together, but there was no audio on it, which is really annoying. So I'm trying to think of the bits that would actually need, like most of it's fine, most of it's fine, just with my writing, I'd say. So I just had to finish off static, which is what's here. The last thing was the energy stored in a charge capacitor. This is just checking it in the formula and tables book, so that's all fine. And then I used it, very straightforward, and that's basically static. Keep going. I then wanted to do chapter 21 because it's very quick. So the first thing in chapter 21 was about the 3 effects of flowing charge, of electric current, which is flowing charge. So there's a diagram here, so not a component diagram because I didn't use the component. Like you can see there, I've drawn the circuit symbol for a battery and I've drawn the circuit symbol for a bulb. They didn't use that. So the first one is the heating effect. So as the current passes through the bulb, I drew it, I think, here. So as the current passes through the bulb, when it's flowing in the wires are thicker, and then when it goes into the bulb, there's like a little skinny piece of wire called a filament. That's what it's going through there. And when it passes through the filament, it's like going from like a 4-lane, like a M50 down to 1 lane. And it's harder for the electrons to pass through. So harder for the electrons to pass through means more resistance. And more resistance causes an increase in temperature. The other thing then is the magnetic effect. So you can see here the compass. So when current flows through the wires, there is a magnetic field. Once there's current flowing, there's a magnetic field around the wires. And if you bring the compass in under the wire, the compass will show the presence of that magnetic field by being affected by it. So the needle will like deflect, I suppose. It'll move from north to south. It will move, not from north to south. It will move from pointing north to south to not pointing north to south. So it'll show that electric current has a magnetic effect. And then the last one is the chemical effect, which you can see in the beaker. So a chemical reaction takes place at each end of the wire, and you can see that from the bubbles. So that's the chemical effect. So because of the flow of electric current through that acidified water, you get a chemical reaction. So that's those 3. That probably needs some talking. Sorry, I know my voice is terrible. Conductors and insulators, I think, is fairly straightforward. And then I go over to the side and show you how you would prove that something is a conductor and something is an insulator. So that's my little circuits there. There I'm just talking about how a voltmeter works. So we talked about that in the last chapter. So a voltmeter is attached across or in parallel across a component. So you'll get the, you get the, it will measure the potential difference on one side of the bulb. No, it'll measure the potential on one side of the bulb, it'll measure the potential on the other side of the bulb, and then the voltmeter will give you the difference or the subtraction. So I'm just reiterating that there. And then down here, what is electric charge? So I literally just draw atom again. So that's that. The electric current is the flow of charge, but if the current or the charge is flowing in a metallic conductor, then it's specifically the flow of electrons. Yeah, so again, we've talked about that before. The unit of electric charge is the coulomb. The size of electric charge, this is a formula. So the size of the current is equal to the amount of charge passing a point per second. And what I was explaining up here, which won't have been clear, this is how I like to think of it. So I like to think of the ammeter as like a little toll booth operator, and the electrons pass him, and it's like how many electrons pass him per second. So if you have a lot of electrons passing him, you have a high current, and if you don't have a lot of electrons passing him, you have a low current. So that's kind of how I like to think about that. Charge an electron is 1.6 by 10 to the minus 9 coulombs. We've used that already, and it's in the formula and tables book. This bit here, again, there's a lot of writing around it, but we've talked a good bit about what's moving in a copper wire, for example. So the charge that's moving in a copper wire is an electron, and we know an electron is negatively charged, which means it moves from the negative terminal to the positive terminal following the red line that I'm now highlighting. But essentially back when it all started, when scientists were working with circuits and they could get bulbs to turn on and buzzers to make noise, they didn't know about electrons. So they knew something was flowing, but they just didn't know what. So they just guessed, and they said that it flowed from positive to negative. And for some reason, it never, we still talk about it. So you'll see in some questions that they talk about the flow of electrons, in which case you need to know that that's in a direction from negative to positive. And in some cases they'll talk about conventional current, and conventional current is basically Benjamin Franklin's incorrect guess, which is that it went from positive, current flows from positive to negative. So you just have to be careful in the question. If the question says flow of electrons, then the direction is negative to positive, and if the question says conventional current, then the direction is positive to negative. So again, obviously I'm writing and stuff around that, but I just wanted to, well, I don't even know if you can hear me. Hopefully you can. Direct and alternating current. So direct current always flows in one direction. So our power supplies, we can choose whether to get alternating current or direct current. A lot of the time in science experiments we use direct current. And then alternating current is what you get when you plug your, like anything really, into the wall. So your mains electricity is alternating. It changes direction every 100th of a second. The next thing here then is measuring current. So like I said, measuring current is like the toll booth operator. So the instrument used to measure current is an ammeter. And again, I draw this here, over here. So here's my circuit, and I want to know what the current is. So you have to put in your toll booth operator so that the electrons pass by him. So you need to break the circuit. So that's what I'm doing there, breaking the circuit and putting in the ammeter. Yeah. So it's called adding it in series, because you have to break the circuit and put it into the paths. So that's been added in series. Over here then it gives you more meters. It's literally just if you want a smaller current to be measured. So if you want a slightly smaller current to be measured, it's milliammeter, and a really small current is microammeter, and then a galvanometer is just another name for a microammeter. So we'll be doing some experiments where we want to use an ammeter, and we'll be doing some where we want to use either micro or milli. Thankfully we have a multimeter which does them all. Next thing here is current in a series circuit, and then current in a parallel circuit. So in a series circuit, go back, sorry, I think I go back up. In a series circuit, basically no matter how many ammeters I put in, provided I break the path and put them in series, they will have the same reading. Whereas if you look, oh, am I going the wrong way? Yeah, if you look down here, so I've highlighted the negative terminal of the battery, and that green arrow shows the direction that electrons will move. What they've indicated using I is current. Clearly that black arrow is in the complete opposite direction, which means that's conventional current. So they've indicated conventional current. Ammeters 1 and 4 are in the series part of the circuit, so they're in the main part of the circuit, which means they will have the same reading. So I think I said that it was reading 10 amps. So if ammeter 4 is reading 10 amps, yeah, then ammeter 1 is reading 10 amps. But there's a whole piece here where ammeter 2 and 3 are, and it's called a parallel arrangement. So you can see that ammeter 2 and ammeter 3 are parallel to each other, so it's a parallel arrangement. So what will happen at that what will happen at that spot there at B, where I've highlighted, is that the current will split up. So if the path where ammeter 2 is and the path where ammeter 3 is are identical, then it will split up perfectly evenly. It will 5 amps go through the top and 5 amps will go through the bottom, and then it will recombine over on the far side. I write it here in a minute. The current will always take the path of least resistance. So if for some reason one of those paths has a higher resistance, so it could be anything, like just more stuff in the path. That might be a bulb, it might be a resistor. If there's stuff in the path that make that path kind of undesirable to the current, then it won't split evenly. Most of the current will go through the path of least resistance. That's what I'm writing there now. Okay, and I think I go on to like put in a bulb or something. Okay, so hopefully that little overview will help make the first video make sense.